Another example of where reflection and interference occur is with thin films. And this is kind of a general category. It could be a lot of things. It could be like soap bubbles. It's kind of like a thin film. You know, a bubble. It's a thin film with air on either side. Or an oil slick, where you just got like a layer of oil on the road, and that then has air and then oil and then something else below it. So those are two kinds of thin films. There are often lots of different colors visible in films. If you've ever seen a soap bubble, you look at it, there's a whole rainbow of colors going on there. And that happens because some light refracts more than others. So at a given location, one color may experience destructive interference, while another will experience constructive interference. And so that color that is experiencing destructive interference is taken out, and then the color that's experiencing constructive interference is enhanced. And so that's why you get those kind of swirling colors that you see in bubbles, or if there's oil on the road. So we'll take a look at how that plays out. So for the case of our bubble, one side of the bubble might look something like this, right? And when we get a light ray that goes in, and it hits our bubble, and it refracts into the bubble, and then some of it reflects off, some of it reflects off this surface, and there's a path length difference. Okay, they use T as the thickness of the film that is too small to see. This thickness is T. That's thickness, not time. Right? So the path length, ray number 1, is going from air and hitting the bubble, which means that our N2, goodness, and I've just realized that these both say the same thing. If N2 is greater than N1, we get a 180-degree phase change. Okay, so when we go off this, going from air into the bubble, the index of refraction in the bubble is greater than in air. So this, if we call this 1, call this 2, this path length for 1, our effective path length, is going to be half a wavelength, because in that reflection, we get a 180-degree phase change. For 2, it just goes boom, boom, and so the effective path length for 2 is just that it traverses the thickness of the bubble twice. So that's the effective path length for 2, so then our path length difference is 2t minus lambda over 2. Alright, so from there, we can write out our conditions for constructive and destructive interference. Or actually, no, we can't quite yet. Hold on. I apologize. And for reasons which will become apparent later, we are going to divide by lambda over here, so that when we get this, what we're going to calculate for thin films, it's a delta lambda over the wavelength. So it's how many wavelengths the path length difference is. Okay. Now the thing is that when we get into this inside of this soap bubble, we're passing through a different material. Now because we're passing through a different material, this wavelength changes. For our air wedge, we were passing through air, which has an index of refraction of 1, so we didn't need to worry about it. But here, this wavelength is the wavelength in the material. So we know that the speed of a wave in some substance is equal to the speed of light over the index of refraction. And likewise, and the frequency doesn't change, so the wavelength is the vacuum wavelength over n. So, if I plug that in then, I've got a delta L over my wavelength is equal to 2t over the vacuum wavelength times n minus a half. vac, B, A, C. All right. And so then, since this is a delta L over wavelength, then we have constructive interference occurring when this path length difference is equal to, 0, 1, 2, 3 wavelengths. So constructive occurs where this 2nt over the vacuum wavelength minus 1/2 is equal to m, where m equals 0, 1, 2, etc. And we have destructive interference,